नमस्कार, मैं आनंद कुमार खत्री। आज के हमारे लेक्चर का विषय है क्लाइमेट पार्ट थर्ड, origin of precipitation in clouds. Cloud formation. Clouds are formed by the lifting of damp air which cools by expansion as it encounters the lower pressure existing at a higher level in the atmosphere. The relative humidity increases until the air has become saturated with water vapor, and then condensation occurs on any of the aerosol particles suspended in the air. A wide variety of these exist in concentration ranging from only a few per cubic centimeter in clean maritime air to perhaps 1 million per cubic centimeter in the highly polluted air of an industrial city. For continuous condensation leading to the formation of cloud droplets, the air must be slightly supersaturated. Among the highly efficient condensation nuclei are sea salt particles and the particles produced by combustion. Many of the larger condensation nuclei over land consist of ammonium sulfate. These are produced by cloud and fog droplets absorbing sulfur dioxide and ammonia from the air. Condensation onto the nuclei continues as rapidly as water vapor is made available through cooling. Droplets about 10 micrometer in diameter are produced in this manner. These droplets constitute a non-precipitating cloud. Cloud types. The meteorologist classifies clouds mainly by their appearance according to an international system similar to one proposed in 1803. But because the dimension, shape, structure, and texture of clouds are influenced by the kind of air movement that result in their formation and growth and by the properties of the cloud particles, much of what was originally a purely visual classification can now be justified on physical ground. This is the cloud types. Different types of clouds forms at different heights. The first international cloud atlas was published in 1896. Development in aviation during World War I stimulated interest in cloud formation and in their importance as an aid in short-range weather forecasting. This led to the publication of a more extensive atlas, the International Atlas of Clouds and States of Sky in 1932, and to a revised edition in 1939. After World War II, the World Meteorological Organization published a new International Cloud Atlas 1956 in 2 volumes. It contains 224 plates describing 10 main cloud genera subdivided into 14 species based on cloud shape and structure. 9 general varieties based on transparency and geometric arrangement also are described. The genera listed according to their height are as follows. This is the high cloud, cirrus fibrous clouds. This is another altocumulus undulatus, middle clouds. This is the low clouds, stratocumulus, stratus cumulus, and cumulonimbus. Heights given are approximate average to for temperate latitude. Clouds of each genus are generally lower in the polar regions and higher in the tropics. The definitions and descriptions of the cloud genera used in the International Cloud Atlas are given in the photograph above and which illustrates some of their characteristics forms. 4 principal classes are recognized when clouds are classified according to the kinds of air motion that produce them. Layer clouds, formed by the widespread regular ascents of air. Layer clouds formed by the widespread irregular stirring or turbulence. Cumuloniform clouds formed by penetrative convection, and orographic clouds formed by the ascent of air over hills and mountains. This is the orography lift, condensation, precipitation, and the rain shadow effect resulting from orographic lift. The widespread layer clouds associated with cyclonic depression near fronts and other inclement weather systems are frequent, composed of several layers that may extend up to 9 km or more, separated by clear zone that becomes filled as rain or snow develops. These clouds are formed by the slow, prolonged ascent of a deep layer of air in which a rise of only a few centimeters per second is maintained for several hours. In the neighborhood of fronts, vertical velocities becomes more pronounced and may each about 10 centimeters per second. Most of the high cirrus clouds visible from the grounds lie on the fringe of cyclonic cloud system, and though due primarily to regular ascent, their pattern is often determined by local wave disturbances that finally trigger their formation after the air has been brought near its saturation point by the large scale lifting. On a cloudless night, the ground cools by radiating heat into space without heating the air adjacent to the ground. If the air were quite still, only a very thin layer would be chilled by contact with the ground. More usually, however, the lower layers of the air are stirred by motion over the rough ground, so the cooling is distributed through a much greater depth. Consequently, when the air is damp, damp or the cooling is great, a fog a few hundred meters deep may form, rather than a dew produced by condensation on the ground. In moderate or strong winds, the irregular stirring near the surface distributes the cooling upward, and the fog may lift from the surface to become a stratus cloud, which is not often more than 600 meters thick. Radiational cooling from the upper surface of fog and stratus clouds promotes air irregular convection within the cloud layer and causes the surface to have a waved or humped appearance. When the cloud layer is shallow, billows and clear space may develop. It is then described or as stratocumulus instead of stratus. Usually, cumuliform clouds appearing over land are formed by the rise of discrete masses of air from near the sunlight warmed surface. These rising lamps of air or thermals may vary in diameter from a few tens to hundreds of meters as they ascend and mix with the cooler, drier air above them. Above the level of the cloud base, the release of latent heat of the condensation tends to increase the buoyancy of the rising masses, which tower upward and emerges at the top of the cloud with rounded upper surfaces. At many moments, a large cloud may contain a number of active thermals and the residues of earlier ones. A new thermal rising into a residual cloud will be partially protected from having to mix with the cool, dry environment and therefore may rise further than its preceders. Once a thermal has emerged as a cloud turret off at the summit or the flanks of the cloud. Rapid evaporation of the droplets chills the cloud board, destroy the buoyancy and produces sinking. A cumulus thus has a characteristic pyramidal shape and viewed from a distance appears to have an unfolding motion with fresh cloud masses continually emerging from the interior to form the summit and then sinking aside and evaporating. In settled weather, cumulus clouds are well scattered and small. Horizontal and vertical dimensions are only kilometers or two. In disturbed weather, they cover a large part of the sky and individual clouds may tower as high as 10 km or more, often ceasing their growth only upon reaching the stable stratosphere. These clouds produce heavy showers, hail, and thunderstorms. At the level of the cloud base, the speed of the rising air masses is usually about 1 meter per second but may reach 5 meter per second, and similar values are measured inside smaller clouds. The upcurrents in thunderclouds, however, often exceed 5 meter per second and may reach 30 meter per second or more. The rather special orographic clouds are produced by the ascents of air over hills and mountains. The air streams is set into oscillation when it is forced over the hill, and the cloud form in the crest of the stationary wave. There may thus be a succession of such clouds stretching downwind of the mountain which remain stationary relative to the ground in spite of strong winds that may be blowing through the clouds. The clouds have very smooth outlines and are called lenticular or wave clouds. Thin wave clouds may form at great heights and occasionally are observed in the stratosphere over the mountains of Norway, Scotland, Iceland, and Alaska. These atmospheric wave form clouds are known as nacreous or mother of pearl cloud because of their brilliant iridescent color. Mechanism of the precipitation release. Growing clouds are sustained by upward air current which may vary in strength from a few centimeters per second to several meters per second. Considerable growth of the clouds droplets is therefore necessary if they are to fall through the clouds, survive evaporation in the unsaturated air below, to fall through below and reach the ground as drizzle or rain. The production of a few large particles from a large population of much smaller one may be achieved in one of two ways. The first of these depends on the fact that cloud droplets are seldom of uniform size. Droplets form on nuclei of various sizes and grows under slightly different conditions and for different lengths of times in different parts of the clouds. Droplets appreciably larger than average will fall faster than the smaller ones and so will collide the fuse with some of those that it overtakes. The calculations show that in a deep cloud containing strong upward air currents and high concentration of liquid water, such a droplet will have a sufficiently long journey along its smaller neighbor to grow to raindrop size. This coalescence mechanism is responsible for the shower that fall in tropical and subtropical region from clouds whose tops do not each reach altitude where air temperature are below 0 degree and therefore cannot contain ice crystals. Radar evidence also suggests that shower in temperate latitudes may sometimes be initiated by the coalescence of water drops, although the clouds may later reach heights at which ice crystals may form in their upper part. The second methods of releasing precipitations can operate only if the cloud top reaches elevation at which air temperature are below 0 degree centigrade and the droplets in the upper cloud region become super cold. At temperature below minus 40 degree, droplets freezes automatically or spontaneously. At higher temperature, they can freeze only if they are infected with special minute particle called ice nuclei. The origin and nature of these nuclei are not known with certainty, but the most likely source is clay silicate particle carried up from the ground by the wind. As the temperature falls below 0 degree, more and more ice nuclei become active and ice crystals appear in increasing number among the supercold droplets. Such a mixture of supercold droplets and ice crystal is unstable. However, the cloudy air is usually only slightly supersaturated with water vapor with respect to the droplets and is strongly oversaturated with respect to ice crystal. The latter thus grow more rapidly than the droplets. After several minutes, the growing crystals acquire falling speeds of tens of centimeters per second and several of them may become joined to form a snowflake. In falling into the warmer region of the cloud, these flakes may melt and hit ground as a raindrop. The deep, extensive, multi-layer cloud system from which precipitations of a widespread, persistent character falls are generally formed in cyclonic depressions low and near fronts. Cloud systems of this type are associated with feeble upcurrents of only a few centimeters per second that last for at least several hours. Although the structures of these great rain cloud systems is being explored by aircraft and radar, it is not yet well understood that such systems rarely produce rain as distinct from diesel unless their tops are colder than about minus 12 degrees centigrade, suggests that ice crystals are mainly responsible. This view is supported by the fact that the radar signals from these clouds usually take a characteristic form that has been clearly identified with the melting of snowflakes. Showers, thunderstorms, and hail. Precipitations from showers, clouds, and thunderstorms, whether in the form of raindrops, pellets of soft hail, or true hailstones, is generally of great intensity and shorter duration than that from layer clouds and is usually composed of larger particles. The clouds are characterized by their large vertical depth, strong vertical air current, and high concentration of liquid water, all factors favoring the rapid growth of precipitation elements by the association of cloud droplets. This is the thunderstorm structures when the atmosphere becomes unstable enough to form large, powerful updrafts and downdrafts. In a cloud composed wholly of liquid water, raindrops may grow by coalescence. For example, a droplet being carried up from the cloud base grows as it ascends by sweeping up smaller droplets. When it becomes too heavy to be supported by the upcurrents, the droplet falls, continuing to grow up by the same process on its downward journey. Finally, if the cloud is sufficiently deep, the droplets will emerge from its base as a raindrop. In a dense, vigorous cloud several kilometers deep, the drop may attain its limiting stable diameter about 6 millimeter before reaching the cloud base and thus will break up into several large fragments. Each of these may continue to grow and attain breakup size. The number of raindrops may increase so rapidly in this manner that after a few minutes the accumulated mass of water can no longer be supported by the upcurrents and falls as a heavy shower. These conditions occur more readily in tropical region. In temperate region where the freezing level 0 degree centigrade is much lower, in elevation conditions are more favorable for the ice crystal mechanism. The hailstones that fall from deep, vigorous clouds in warm weather consist of a core surrounded by several alternate layers of clear and opaque ice. When the growing particles traverse a region of relative high air temperature or high concentration of liquid water or both, the transfer of heat from the hailstone to the air cannot occur rapidly enough to allow all the deposited water to freeze immediately. This results in the formation of a wet coating of slushy ice which may later freeze to form a layer of compact, relatively transparent ice. If the hailstone then enters a region of lower temperature and lower water content, the impacting droplets may freeze individually to produce ice of relative low density with air space between the droplets. The alternate layers are formed as the stone passes through a region in which the combination of air temperature, liquid water content, and updraft speed allows alternately wet and dry growth. It is held by some authorities that lightning is closely associated with the appearance of precipitations, especially in the form of soft hail, and that the charge and the strong electric fields are produced by the ice crystals and clouds droplets streaking and bouncing off the undersurface of the hail pellets. For a detailed discussion of electrical field effect in clouds. Type of precipitation: drizzle, liquid precipitation in the form of very small droplets with diameter between 0.2 and 0.5 millimeter and terminal velocity between 70 and 20 centimeter per second is defined as a drizzle. It forms by the collisions of even smaller droplets in low layer clouds containing weak drafts of only a few centimeter per second. High relative humidity below and cloud base is required to prevent the drops from evaporating before reaching the ground. This is classified as slight, moderate, or thick. Slight drizzles produce negligible runoff from the roof of the building, and thick drizzles accumulate at a rate of excess of 1 millimeter per hour. Rains and freezing rain. Liquid water drops with diameters greater than those of drizzle constitute rain. Raindrops rarely exceed 6 millimeters in diameter because they become unstable when larger than this and break up during their fall. The terminal velocity of raindrops at ground level range from 2 meters per second for the smallest to about 10 meters per second for the largest. The smaller raindrops are kept nearly spherical by surface tension forces, but as the diameter surpasses about 2 mm, they become increasingly flattened by aerodynamic forces. When the diameter reaches 6 mm, the undersurface of the drops becomes concave because of the air streams, and the surface of the drop is sheared off to form a rapidly expanding bubble or bag attached to an annular ring containing the bulk of the water. Eventually, the bag bursts into a spray of fine droplets, and the ring break up into a circlet of millimeter sized droplets. This is a rain shaft piercing or tropical sunset. Rain of a given intensity is composed of a spectrum of drop size, the average and median drop diameter being larger in rains of greater intensity. The largest drops, which have a diameter greater than 5 mm, appear only in a heavy rains of intense storms. When raindrops fall through a cold layer of air and become super cold, freezing rain occur. The drops may freeze on impact with the ground to form a very slippery and dangerous glazed ice that is difficult to see because it is almost transparent. Snow and sleet. Snow in the atmosphere can be subdivided into ice crystals and snowflakes. Ice crystals generally form on ice nuclei at temperature appreciable below the freezing point. Below minus 40 degrees centigrade, water vapor can solidify without the presence of a nucleus. Snowflakes are aggregates of ice crystals that appear in an infinite variety of shapes, mainly at temperatures near the freezing point of water. In British terminology, sleet is the term used to describe precipitation of snow and rain together, or of snow melting as it falls. In US, it is used to denote partly frozen ice pellets. Snow crystals generally have a hexagonal pattern, often with beautifully intricate shapes. 3 and 12 branched forms occur occasionally. The hexagonal form of atmospheric ice crystals, their varying size and shape notwithstanding, is an outward manifestation of an internal arrangement in which the oxygen atoms form an open lattice with the hexagonally symmetrical structure. According to a recent internationally accepted classification, there are 7 types of snow crystals: plates, stellar columns, needles, spatial dendrites, capped columns, and irregular crystals. The size and shape of these snow crystals depends mainly on the temperature of their formation and on the amount of the water vapor that is available for deposition. The two principal influences are not dependent. The possible water vapor admixture of the air decreases strongly with the decreasing temperature. The vapor pressure is equilibrium or state of balance with a level surface of pure ice is 50 times greater at minus 2 degrees centigrade than at minus 42 degrees centigrade. The likely limits of snow formation in the air. Crystal shapes and temperature of at formation are related in the table. At temperature above about minus 40 degrees centigrade, the crystals form on nuclei of very small size that float in the air The nuclei consist predominantly of silicate minerals of terrestrial origin, mainly clay minerals and micas. At still lower temperatures, ice may form directly from water vapor. The influence of the atmospheric water vapor depends mainly on its degree of supersaturation with respect to ice. If the air contains a large excess of water vapor, the snow particle will grow fast and there may be a tendency for dendritic growth, branching growth. With low temperature, the excess water vapor tends to be small and the crystals remain small in relatively dry layer. The snow particles generally have simple forms. Complicated forms of crystals will cling together with other to form snowflakes that consist occasionally of up to 100 crystals. The diameter of such flakes may be as large as 2.5 centimeter. This process will be further if the crystals are near the freezing point and wet, possibly by collision with undercooled water droplets. If a crystal falls into a cloud with great number of such drops, it will sweep some of them up. Coming up into contact ice, the freezing and form an ice cover around the crystal. Such particles are called soft hells. Snow particles constitute the clouds of cirrus type, namely cirrus cirrostratus and cirrocumulus, and many clouds of alto type. Ice and snow clouds originate normally only at temperatures some degree below the freezing point. They predominate at minus 20 degrees centigrade. In temperate and low latitude, these clouds occurs in the higher layer of the troposphere. In tropical regions, they hardly ever occur below 4570 meter. On the high mountains and particularly in polar regions, they can occur near the surface and may appear as ice fogs. In cold air near the ground is overlain by warmer air. Mixture at the border leads to supersaturation in the cold air. Small ice columns and needles, diamond dust will be formed and will float down. Glittering even form a cloudless sky. In the cloudiest part of Antarctica, where temperature near the surface are below minus 50 degree on the average and rarely above minus 30 degree, the formation of diamond dust is a common occurrence. The floating and falling ice crystals produce in the light of the sun and the moon the manifold phenomena of atmospheric optic halos, arcs, circles, mock suns, some coronas, and iridescent cloud. Most of the different optical appearance can be explained by the shape of the crystals and their position with respect to the light source. Most of the moderate to heavy rain in temperate latitude depends on the presence of ice and snow particles in clouds. In the free atmosphere, droplets of fluid water can be undercooled considerably. Typical ice clouds originate mainly at a temperature near minus 20 degree. At an identical temperature below the freezing point, the water molecules are kept more firmly in the solid than in the fluid state. The equilibrium pressure of the gaseous phase is smaller in contact with ice than with water. At minus 20 degrees centigrade, which is the temperature of the formation of typical ice clouds cirrus, the equilibrium pressure with respect to super undercooled water is 22% greater than the equilibrium pressure of the water vapor in contact with ice. Hence, with an excess of water vapor beyond the equilibrium state, the ice particles tend to incorporate more water vapor and to grow more rapidly than the water droplets. Being larger and so less retarded by friction, the ice particles fall more rapidly in their fall. They sweep up some more droplets, which on contact become frozen. Thus, a cloud layer originally consisting mainly of undercooled water with few ice crystals is transformed into an ice cloud. The development of the unveil shape at the top of a towering cumulonimbus cloud so this transformation very nearly. The larger ice particle overcome more readily the rising tendency of the air in the cloud. Falling into lower level, they grow aggregating with other crystals and possibly with droplets melt and other and from raindrops when near surface temperature permit. Hail. Solid precipitation in the form of hard pellets of ice that fall from cumulonimbus cloud is called hail. It is convenient to distinguish between three types of hail particles. The first is soft hail or snow pellets, which are white, opaque, rounded, or conical pellets as large as 6 millimeter in diameter. They are composed of small cloud droplets frozen together, have a low density, and are readily crushed. The second is small hail ice grains or pellets, which are transparent or translucent pellets of ice that are spherical, spheroidal, conical, or irregular in shape with diameter of a few millimeter. They may consist of frozen droplets of largely melt and refrozen snowflakes or of snow pellets encased in a thin layer of solid ice. True hailstones, the third type, are hard pellets of ice larger than 5 millimeter in diameter. They may be spherical, spheroidal, conical, discoidal, or irregular in shape and often have a structure of concentric layer of alternately clear and opaque ice. A moderately severe storm may produce stones a few centimeters in diameter, whereas a very severe storm may release stones with a maximum diameter of 10 centimeter or more. Large damaging hail falls most frequently in the continental areas of middle latitude, but is rare in equatorial region. Terminal velocity of a hailstorm range from about 5 centimeter per second for the smallest stones to perhaps 40 centimeters per second for stones 5 centimeter in diameter. Word distribution of precipitations. Regional and latitudinal distribution. The yearly precipitations averaged over the whole earth is about 100 centimeter, but this is distributed very unevenly. The regions of highest rainfall are found in the equatorial region and monsoon area of Southeast Asia. Middle latitudes receives moderate amounts of precipitation, but little falls in the desert region of the subtropics and around the poles. If Earth's surface were perfectly uniform, the long-term average rainfall would be distributed in distinct latitude bands. But the situation is complicated by the patterns of the global winds, the distribution of land and sea, and the presence of mountain because rainfall results from the ascents and cooling of moist air, and the areas of the heavy rain indicate region of the rising air, whereas the deserts occur in this region in which the air is warmed and dried during descent. In the subtropics, the trade winds bring plentiful rains to the east coast of the continent, but the west coast tend to be dry. On the other hand, in the high latitude, the west coasts are generally wetter than the east coast. Rain tend to be abundant on the windward slopes of the mountain ranges but sparse on the lee sides. In the equatorial belt, the trade winds from both hemispheres converge and give rise to a general upward motion of air, which become intensified locally in tropical storms that produce very heavy rains in the Caribbean and Indian and Southwest Pacific Ocean and the China Sea in the thunderstorms that are especially frequent and active over the land areas. During the annual cycle, the doldrums move towards the summer hemisphere. So, outside a central region near the equator, which was abundant rain at the all season, there is a zone that receive much rain in summer but a good deals less in water. This is the word pattern of thunderstorms frequency. The dry areas of the subtropics, such as the desert region of North America, the Arabian Peninsula, South Africa, Australia, and Central South America, are due to the presence of semi permanent subtropical anticyclones in which the air subsides and becomes warm and dry. These high pressure belts tend to migrate with the seasons and cause summer dryness of the poleward side and winter dryness on the equatorward sides of their mean position. The easterly trade winds, having made a long passage over the warm ocean, bring plentiful rains to the east coast of the subtropical landmass, but the west coast and the interior of the continent, which are often sheltered by mountain range, are very dry. Effect of precipitation: raindrop impact and soil erosion. Large raindrop up to 6 millimeter in diameter have terminal velocity of about 10 meter per second and so many cause considerable compaction and erosion of the soil by their force of impact. The formation of a compact crust makes it more difficult for air and water to reach the roots of plants and encourage the water to run off the surface and carry away the topsoil with it. The surface runoff: the rainwater that is not evaporated or stored in the soil eventually run off the surface and finds its way into rivers, streams, and lakes, or percolate through the rocks and become stored in natural underground reservoir. All the waters that falls on the earth's surface, the relative amounts that run off, evaporate, or seep into the ground vary so much for different areas that no firm figure can be given for earth as a whole. Thanks.